Light moves so fast that, for most of our history, we assumed it didn't take any time at all to travel. If you light a candle in a dark room, the space is simply illuminated. There is no perceptible delay. Ancient philosophers debated whether light was a physical substance or something more like a state of being. To them, the idea of measuring its speed was as nonsensical as measuring the speed of a thought. It was considered instantaneous. But to truly understand the universe, we eventually had to find out if light had a limit. In 1638, Galileo Galilei proposed one of the first recorded experiments to test this. He and an assistant stood on two different hilltops about a mile apart, each holding a shuttered lantern. Galileo would open his lantern, and as soon as the assistant saw the light, he would open his own. Galileo tried to measure the time it took for the light to travel the round trip. However, the speed of light is so great that any delay he measured was simply human reaction time. He concluded that if light wasn't instantaneous, it was at least extraordinarily fast. The first real breakthrough came nearly 40 years later, and it didn't happen on Earth. Danish astronomer Ole Rømer was studying Io, one of Jupiter's moons. He noticed something strange. The timing of Io's eclipses changed depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened sooner than predicted. When Earth moved to the opposite side of the Sun, they were delayed. Rømer realized this wasn't a problem with the moon's orbit, but rather that light took more time to cross the extra distance of Earth's wider orbit. By calculating these delays, Rømer estimated that light took about 22 minutes to cross the diameter of Earth's orbit. While his final calculation was about 25% off from the modern value, mostly because the distances between planets weren't perfectly known yet, it was a monumental discovery. It proved that light had a finite speed. It was no longer an abstract quality. It was a physical phenomenon that moved through space over time. For the first time, we had a rough idea of the sheer scale and speed of the solar system. In the 1720s, James Bradley refined this using a phenomenon called the aberration of starlight. Imagine walking through a vertical rainstorm while holding an umbrella. To stay dry while moving, you have to tilt the umbrella forward. Bradley noticed that telescopes had to be tilted slightly to capture light from stars because the Earth was moving through space. While measuring this tiny tilt, he calculated light speed with much greater accuracy. He arrived at a figure of about 301,000 kilometers per second, remarkably close to the actual value we use today. Until the mid-19th century, all measurement relied on observations in space. Hippolyte Fizeau wanted to measure light speed entirely on Earth. In 1849, he set up a clever apparatus, a rapidly spinning cogwheel, and a mirror located 8 kilometers away. He shone a beam of light through the gaps in the cog. As the wheel spun faster, the light returning from the mirror would eventually hit one of the teeth instead of passing back through a gap. By knowing the speed of the wheel and the distance to the mirror, Fizeau could calculate the time of flight. Léon Foucault improved this by replacing the cogwheel with a rotating mirror. This allowed for measurements over much shorter distances, even inside a laboratory. Later, Albert Michelson refined this further, using a high-speed rotating octagonal mirror across a 22-mile gap between two mountains in California. Michelson's obsession with precision lasted decades. He realized that to get the perfect number, he had to account for everything, even the temperature and pressure of the air, which slightly slows light down. He eventually performed the experiment inside a mile-long vacuum tube to remove all interference. While experimentalists were perfecting their tools, theorists were discovering why light moves at that specific speed. James Clerk Maxwell formulated the equations of electromagnetism and found that the speed of an electromagnetic wave was determined by two fundamental properties of space: how it resists electric fields and how it resists magnetic fields. When he calculated the speed these waves should travel, it matched the measured speed of light perfectly. This revealed that light wasn't just fast, it was a fundamental interaction of the very fabric of our universe. At the turn of the 20th century, Albert Einstein took this a step further. He realized that if the speed of light is a fundamental property of the universe, it must be the same for everyone, regardless of how fast they are moving. This cosmic speed limit became the cornerstone of his theory of special relativity. It means that light doesn't just travel through time and space, it dictates how they behave. To keep the speed of light constant for all observers, time itself must slow down and space must contract as you move faster. By the 1970s, our measurements became so precise that the limiting factor was no longer our timing of light, but our definition of a meter. In 1983, the scientific community did something radical. They stopped measuring the speed of light. Instead, they fixed its value at exactly 299,792,458 meters per second. Now, we use light to define distance. 1 meter is officially the distance light travels in a vacuum in a tiny fraction of a second. The speed of light became the fixed yardstick for our entire physical reality. Looking back, the journey to measure light is a story of human persistence. We went from waving lanterns on hills to using the entire solar system as a laboratory, and finally to redefining our fundamental units of measurement around it. Light is the fastest thing in the universe, but it isn't infinitely fast. That limit, that slight delay, is what allows the universe to have a history and a structure. By catching the fastest thing we know, we didn't just find a number, we found the rhythm of the cosmos itself.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.